be giving us those A values. Okay? All right. I should probably have an A up there, should I? Since I put an amplitude of A over here. Okay. So now, this equation fundamentally recognizes that I have these 2D distributions centered at each of A, JA, minus A, and minus JA. So for my maximum likelihood equation, each of those individual f of y given thetas is essentially almost, I like to think of this stuff as contours, okay? When I'm thinking about a plane here, you got a peak, a little mountain peak on there, and then it just kind of drops down slowly in a Gaussian fraction and goes off to infinity in each direction. So we have 4 of those, where the peak is at a different location. They're just rotations of one another in this particular case. Okay? And all we're doing is, once again, we're going to lay those guys together and decide at every given point which one of these distribution functions has the maximum value. So in our particular case, that is going to lead to the very convenient, I guess you could say, observation that the boundary condition is going to end up being at the 45s. Okay? If I am now somewhere in this 90-degree angle, or this 90-degree angle, or this 90-degree angle, or this 90-degree angle, then I'm going to pick that corresponding peak. Because that is where one of those distributions starts to be lower than the other distributions, okay? That's that one location, that's that boundary condition. So therefore, when you have n-area phase shift key, your boundaries for your decisions are simply just dividing up the plane into the corresponding number of equal height edges. And then, when I receive a vector that points out here, well, I'm in the wedge corresponding to the minus A, so that is the value that's going to maximize my likelihood equation. I'm no longer taking a ratio because I don't have a pair of values. I can't really have a binary decision test or a binary hypothesis. This is why at the end of the day, we say this is the argmax over theta, and that's the y of y given theta in this case, okay? Or x, whatever, doesn't matter. I am now, yeah, I guess x here, technically speaking. Because now I have an observation, I find out the theta that is most likely to produce this value. And given that I have this circulating symmetric Gaussian noise, that's the quadrant I landed in. This should be really intuitively obvious in terms of how these lines are drawn. What I recognize is not necessarily trivial to get there in the math. I hope that conceptually, if I had just said, you have these 4 possible values, how are we going to decide if a value in this plane corresponds to one of these? I would hope that most of you would have just drawn the x at 45s. Okay? That should have been your kind of natural, intuitive reaction. And if so, then you get MLE. Because that's fundamentally what MLE is doing. Alright? It's finding that inflection point. It's finding that point, and now my previous distribution ceases to be the highest. And then from that point on, I just pick whatever is the highest for that spot.
Just keep pretending to drink and making thirsty.
You're not fast enough, Kevin.
It's okay, it's recorded.
Okay, that makes sense. Everybody got that. So that should be pretty simple. Now, what's interesting is, once again, here we didn't care what was the probability that we would have gotten any of the other particular values. Okay, we're just as fundamentally assuming here everything is equally likely, and therefore we are making a comparison among those possible values. So now, let's look in detail at maximum A posteriori estimation. Now so what we did here is we found the maximum theta, the theta that maximized our probability distribution is the x that was transmitted given our observation. Or our observations are given the possible transmittance. There we go. Proper statement. Okay, the observation given the possible transmittance. Fundamentally, what this is doing is going to be, realistically, argmax over theta of x joint with theta. Okay? This is subtly different. The key point. This is subtly different. But instead of now looking just at the conditional, so comparing each of those distributions individually and deciding which one is maximal, we're now going to be saying what is the most likely combination of x and theta. So this will now take into account the probability that each of our signals was transmitted. So let us look at this. So basically it's just NLE, but we're now accounting for the input of the distribution. Like NLE, we're now accounting for input distribution, okay? That's what we're doing. All right. So, let's go back to our n equal to 2 case. This guy here. Okay. Okay, so n equal to 2 case. Now, what we're going to do here then is we're going to say that our theta hat is equal to the argmax over our theta space, over theta, of effectively it's hard to get to this. Okay. The joint probability of our x or y and our theta. Okay? So we had f of y given theta in this particular case was equal to 1 over sigma n root 2 pi e to the minus y minus theta squared over 2 sigma n squared. Okay, so theta, remember, is in the space A and minus A here. All right? Then, we have some probability mass function for theta, if you recall, which was equal to P for theta equal to A, and 1 minus P for theta equal to minus A, and 0 else. Okay, that was our PMF. All right? So, the joint distribution, if you recall by total probability theory, can be rewritten. So in this case, E of y theta can be rewritten as the probability of y given theta, the sum over all the theta sub I, E theta sub I. Okay? Conditional distribution, and then the marginal of theta. So with familiar people, we say yes. Good, okay. So what that means here is my joint distribution that I need to maximize is fundamentally going to be P times 1 over sigma n root 2 pi e to the minus 1 minus a squared over 2 sigma n squared plus 1 minus p 1 over sigma n root 2 pi e to the minus y plus a squared over 2 sigma n squared. Okay? All right. Now, what I really want to do, though, is let's try to go back one moment, and let's say, more usefully, what is the probability density of y? Yeah, don't let me do your I see now why you use G. So now let me define, just to make this work. So this is not necessarily going to be trivial, because I don't really have theta in here anymore, right? I don't have a theta. I have A and minus A. So fundamentally, we kind of don't want to use this function for this particular solution. So let us instead, okay, so let me just note, hard, no theta left. Okay. Let's now define G of y and theta to be equal to f sub y of y given theta. Let's go back to conditional. The P and F of theta, or that given theta, all over f sub y of y. So technically speaking, what have I done here? I'm simply converting this, for those who do not recognize it, into P of theta given y. Okay? Because I'm creating in the top the joint distribution of y and theta and dividing by the marginal probability of y, which gets me theta given y. Okay? So let's get this for a second here. This turns out, we can write these equations, becomes then e to the minus y minus a squared over 2 sigma n squared all over that guy, which I'm not going to rewrite. Okay? Or theta equal a. And then it is e to the minus y plus a quantity squared over 2 sigma n squared over that big mess, or theta equal to minus a, and of course 0 elsewhere. Okay? So now I have two marginal distributions, or two conditional distributions arguably, and I can once again use a ratio test. Because of the fact that if A is equal to A, then this guy should end up giving me a larger value. And if theta is less than equal to negative A, the denominator should end up giving me the larger value. So let's compute then L of y to be G of y comma theta equal to A over G of y theta equal to minus A. And we'll be comparing that once again to 1, where greater than 1 will be viewed as A, less than 1 will be viewed as minus A. And it turns out that if we go through and do all those divisions, our denominator politely drops out, which is part of the reason I haven't bothered to recopy it. And I'm just left with my numerators, which end up being P times E to the y minus A squared over 2 sigma n squared over 1 minus P e to the minus y plus A quantity squared over 2 sigma n squared. Okay? Which is not necessarily pretty, but let's expand that for just a moment. Math is generally mathematically not pretty, but conceptually at the end it will make some sense to you. So, L of y then can be written as P over 1 minus P times e to the minus 1 over 2 sigma n squared times minus y squared plus 2ay minus a squared plus y squared plus 2ay plus a squared greater than or equal to 1. A minus A. Okay? So this all works out to be, if we then take the natural log, the log likelihood now, I'm going to put my 1 minus P and P on the other side, or minus P over P, natural log of that quantity. Gets rid of my E on the left-hand side. Once again, y squared, o squared cancel out, and I'm going to get 4ay. So now, my y is going to be a minus a 1 or 2. Oops, I missed the sigma n squared, thank you. 2 sigma n squared, yes. 2 sigma n squared over for A, so sigma squared over 2A times the natural log of 1 minus P over P. Okay? This, then, is going to be my map criterion. Now, a quick observation. If P is 1/2, what does that right-hand side become? 0. Okay? For P equal to 1/2, map goes to MLE. In other words, equal probability, which is basically what I said earlier. If everything's equal, we end up with the MLE answer. We get that same nice result. Okay? Otherwise, what's really happening is that we now have a function that is going to scale. So instead of having two separate functions that we're comparing on an independent basis, plot one where the area under is 1, plot the other where the area under it is 1, and just make a comparison of which one's higher at any given point, we now have, in effect, scaled versions of these guys. And they're being scaled here partially by P, partially by sigma, and partially by our A. In effect, we're getting a ratio here in the front, the inverse of which is going to be at least proportional to, not equal to, but proportional to our signal to noise ratio. Okay? The inverse of it, all right? So, if we're going to draw this, where's over there now? Try to accumulate them all to the left. Figures. Okay, so avoiding the chocolate over the place in yours.
Seasoning.
Pardon? Seasoning. Okay. So what's happening now is that as P goes up, this right guy, because he's going to become more likely, dominates. So that really means that in effect, he becomes higher, and this little guy becomes lower. So my decision point goes this way with increasing P. If P becomes less likely, then my decision point will move to the right with decreasing P. Okay? Sorry, so this means increasing and decreasing, not necessarily positive and negative. Okay? So P greater than 1/2, let's say. P less than 1/2. So that is how we're going to do this. And so at the end of the day, we are still going to be picking as a decision point that inflection location. Because fundamentally, intuitively, that makes sense. We're still looking for one of the density functions, conditional density functions, to be greater than the other. Because it doesn't make sense to do anything else. So, from a practical comparison purpose, we're in that silo in South Dakota. If we're doing an MLE, we're doing a decision based on the observation y being greater than or less than 0, right? And it doesn't matter in that case that the not A condition is by far the most common thing you're ever going to get. Okay, so we hope that in real life minus A, occurs with, probability 0.9999 something or other. And we hope that A only occurs with a probability of, 0.00001 or so, okay? Put a bunch of zeros in front of that, right? Okay? The MLE estimator doesn't care. It says if I receive anything that's 0.00001, I need to turn the key and blow the roll. That's what it wants. And that means it's done. It's assuming they're equally probable. In this particular case, if we did, for example, a maximum a priori estimator, we would always pick minus A, because minus A is always more likely to be transmitted. We would never, ever turn the key, even when we did get the signal. It may not be bad, but at the same time, it might not be a good thing. So, a priori would say whatever is most likely. Now, in this case, that's a little excessive, but again, as I talked about last time before we decided what's your a priori grade, well, I know the distribution of grades in the class is going to have C being the most common grade, and the a priori estimate of your grade is a C. Okay? You may not like that, or you may be happy with that, but that's what it's going to be. Our max a posteriori now, in this particular case, is going to vary depending upon everything, but we are going to end up with our equation over there, which will be y greater than or equal to whatever our sigma n squared is over whatever our amplitude is times 2. And the natural log of, well, p is ridiculously small, so this is a 0.9999, correct? Or remember? Yes, okay. So this is basically going to be 0, but not quite. Okay? In this case, they'll be almost the same thing because of... Okay, so we're going to get this value. If we bring these guys... Oh, sorry, not 899, 999, there we go. Big value. So now, this builds in safety, because this says we don't pick A until Y is basically huge. The natural log of 99,999 times whatever that preceding coefficient is. So here, here's 0, here's minus A, here's A, here's my MLE, here's my maximum a priori, and then, to be honest, odds are very good that my map estimator is somewhere out here very close to A. I need to get A for all intents and purposes, or I ain't picking it. That's what it says. Does that make some sense to people? This is how they interact. Map is going to take into account the prior probabilities and shift the decision point so that you are less likely to make an error. MLE assumes everything's equal. Just divide up your space nice and evenly, and you're all set. You've already done MLE. And maximum a priori is pick whatever is most likely and just say that's it no matter what. Okay? All right. So that covers a whole bunch of estimations.